winter break. It was freezing here. We were outside the habitable zone of the sun for the first time in my memory, at least. It was -20. Actually, the deep freeze in our garage sounded the alarm because it was supposed to warm the food relative to the background temperature. The manufacturer never designed it to do that. It was -20 Celsius for a couple of weeks. Yeah. So that was pretty bad. But we got a good sense of what it's like to be in the South Pole.
The car didn't start then, is it?
Sorry?
Did you have problems with the cars? I mean the car. No. Because I thought that
It worked.
amazing.
Yeah.
My car didn't work.
It was probably BMW or something like that.
I guess it depends on the car. We actually have a virtual seat here, as you can see, with Peter Gallison sitting on it through a laptop. Peter is joining us through Zoom, which is a very convenient form of communication these days, and he's on sabbatical in North Carolina throughout the semester. Actually, I realized that almost all of the BHI faculty were on sabbatical this year. Yao is just back, and he will be the first speaker, but Ramesh is on sabbatical, he's away this week. Andy is on sabbatical. You're off sabbatical now? You're back?
I should have said that.
Okay, that's great. So actually, Andy, since you said that you're here, there is an interesting question that I was discussing with Juan Maldacena, and maybe you have an insight. Since this is the black hole initiative, what happens to an electron, which is considered to be a point particle, in string theory or any other theory that you prefer, when it gets close to the singularity? I mean, how would you describe a single particle, point particle, classical or quantum mechanics, as it gets close to where the curvature diverges, according to Einstein's GR? Is there a discussion on that question?
I think we can't. I think we can't because we know that GR must get corrected in a way that becomes arbitrarily large. So any theory that we have, nobody has ever come up with a theory that enables us to systematically answer that question.
Well, but in string theory, if you think of it as a string,
in string theory, we've been able to answer that question for the case of time-like singularities, not like the ones in Schwarzschild, but like the ones in Riester-Nordström. And then for certain kinds of string-theoretic black holes, we could say as much as you wanted about what happens.
And that was discussed, or not?
That's been discussed, yeah. Okay. But the space-like singularities are just, it's a big problem. It's a big problem to find in fact, people who studied the ectorotic were interested in that problem, and there were a few steps taken at it in that context, not very different context, and
yeah. So there is a lot of discussion on string cosmology about the singularity of the Big Bang, but there isn't as much discussion on black hole singularities.
Well,
for some reason,
the Big Bang problem is a little bit simpler because there's more symmetry. But even that one, there aren't hard results.
Thank you. So today we have, as usual, a busy program, and we have two or three talks. Two. And we'll start with Yao, but who would like who is presenting Yao? You are? Yeah. Okay, go ahead.
Yes. So we're very happy for our first talk of the year to have as CEO. I guess everyone already know Yao, but let me just say he's a professor of mathematics at Harvard University and a faculty member here at the Black Hole Initiative. And he has made very fundamental contribution to differential geometry which have found deep implication in astronomy and in theoretical physics, and it was awarded the Fields Medal in 1982. So we are very happy to have him talk today at the BHI about quasi-local mass in GR.
Thank you.
Actually, I didn't realize I'm supposed to give a talk today until I was told by you. Anyway, so this talk will be accumulation of talks that works by many people, many of my students and postdocs. So we start from an isolated gravitational system. So it will be described in a three-dimensional formulation. So there's a slice of the space-time, which is M. There's a metric, and also the second-dimensional form, which describes how it moves vibrates in space-time. And we shall assume it's asymptotic flat in the sense that it's near infinity, everything becomes trivial. But that actually is non-trivial question because how to measure it to be asymptotic flat. So out to minus q where q is positive, and so it's very close to Euclidean metric. And the k is this k will be close also going down to 0 and infinity, r to the power minus q. P plus q in general would be bigger than 3. But that's only because we know what to do in that case. In general, there's no reason why P plus Q should be bigger than 3, I think, because it's just, the only reason is that technically it's easier. In any case, from the way the Einstein equation writes, the mass density associated to this data.
Are you assuming here this is embedded in? It says spatial infinity, not null infinity.
We just say spatial infinity at this point. We start out from the initial data only. We don't know what the future looks like.
But they're asymptotically flat slices that go to null infinity. I guess there's some constraint on k, so that they can't be one of those.
K goes down to 0, so it's spatial infinity.
Yeah.
So this mu is the mass density as measured in this data, and R is a scalar character of this metric, and this is K is this K, and J is the current density, which supposedly decay pretty fast under those assumptions. So we use this as the initial data for Einstein equation, and we evolve this data. This is the initial data formulation. We like to see that how the things looks like at infinity, and we hope that we can understand what's going on in the future, but it's not a trivial problem at all. And under reasonable condition on the space-time, my former student Robert Barnett proved that there exists a maximal space-time hypersurface. So maximal hypersurface is the case where the trace of k equals 0. So you maximize space volume locally, and this becomes an important statement because everything becomes much nicer on the maximal space-time hypersurface, at least from geometric point of view. And it seems that they try to avoid singularity. It really is. But he proved it under something what we call reasonable condition. Unfortunately, the reasonable condition is assuming how black hole looks like in some way, which we like to avoid if we want to understand black hole. But in any case, under the reasonable assumption that we know about what black hole is supposed to be like K or whatever, then one can prove existence of maximal space-time hypersurface. In this case, trace of K would be equal to 0. Otherwise, in the cosmology case, we assume trace K to be constant, and this has been a useful framework. Well, then one would like to understand, one evolve to infinity, want to see how it looks like in the now infinity also. This becomes a little bit different problem. What I'm trying to do today is talking about quasi-local mass, where I want to understand how to evolve the Einstein equation based on initial data. The mathematical way to demonstrate this kind of evolution dates back to much earlier, Shing-Tung Yau, and also later by Quasilocal. Is always using something called energy method. So you want to see how the total energy looks like in the initial data, and you want to see how it evolved in time, and you want to say that it's not blowing up, and then you control how the data would be. But those are rather difficult way to do it, because it doesn't see the actual nature of the Einstein equation, because those energy is not defined according to Einstein equation supposed to mean. It depends on the choice of gauge and all that. So I like to avoid that. And anyway, so we like to deal with this problem by looking at quasi-local mass. First of all, we know I did something with Hodgkin about 30 years ago. If the mass of a slice is positive, which is known to be true, I proved with Hodgkin there's a unique family of foliation by sphere of constant mean curvature of the slice near infinity. So in fact, near infinity, there's a well-defined frame near infinity by using this foliation sphere, and it's unique. And this is true only when the mass is strictly positive. This is not true in Euclidean space. In Euclidean space, you have all kind of sphere going out in infinity, wobble around. But in the case of strictly positive mass, there's exactly one foliation. This is actually a very important statement, I think. In this setting, there actually exists a canonical coordinate near infinity. And this should be important for computation in general relativity. But anyway, now I'm trying to understand, for example, a simple phenomena when you bubble or merging black holes, when domains coming and all that. I will understand what the total mass enclosed by the domain compared with each individual mass, so that we can define what binding mass is and all that. And that we need to know the concept of quasi-local mass. And this is what I'm going to talk about today. Now, a very important tool that we need to use, and this is also a tool that we use to find a apparent horizon. This was developed by Richard and myself many years ago, 40 years ago, is that given a three-dimensional slice, we want to find out where the apparent horizon is. Not event horizon, but the apparent horizon. What we do is that we solve this equation. We try to solve this equation, where f is unknown. And by looking at the points where f blows up, it gives rise to exactly where the apparent horizon is. And this actually should be important for numerical calculation, because this gives you a tool to find out exactly where the apparent horizon is when you know nothing about it. At the beginning, everything is non-singular. You want to know where the apparent horizon is so that you can find where the singularity would be. We developed a tool to discover it by looking at this equation. And we proved that if any apparent horizon can be found as a level set given by f. So this is an important tool, and we make use of it for both numerical and also theoretical study. Okay. Anyway, so apparent horizon can be looked at, and we can deal with that, but let's not go into that too much now. Now, for a closed surface enclosing a spatial region, the Lagrangian formulation of GR using three-dimensional ADM formulation, we can find the definition of a surface Hamilton can be written in this form. Now, this is important. So, W nu is a future timeline unit vector field along S that corresponding to translation to the future. And we write this translation, this observer, so W mu can be looked at as observer, is moving in this way, is decomposed into the normal direction, this is called the Left function, and this is called the C vector. This is the projection on the surface itself. Now, then we write the space-like unit normal orthogonal mu along S, so the S is supposed to enclosing a three-dimensional D, so there's a normal vector for the surface sitting in D. And this gives rise to two things. The mean curvature of the S with respect to this normal vector. And P is the second fundamental form of D itself, the three-dimensional space. And you write it down to be this form. Now this all integrate over the surface. So we like to call this the entity of the surface, but it depends on several things, which depend on choice of gauge. Namely, n is the Lex function, which depends on choice of gauge. This one is a mean character, is independent of choice of gauge. N mu is a shift vector, depends on this projection, which depends on choice of gauge. And P mu nu actually depends on choice of the three-dimensional gauge. We are choosing a three-dimensional domain that is enclosed. So all this depending on choice of gauge. So although I like to define this one to be the entity because it's a surface Hamilton derived completely from the Lagrangian formulation, it's not actually quite well defined. So some people at the beginning it was Brown and Yau, and then later Hawking, Horowitz, and several people simply take the choice n equal to 1 and n equal to 0. So you just take the observer to be always normal to the surface, which is depending on the choice of gauge. Okay. So this is not completely satisfactory, but although it is actually quite good in many ways. So I will come back to that statement first. First of all, in that case, there are many important quantities that we want to base on this gauge. Based on this quantity that I just mentioned, to try to derive and try to make it to be understandable, drawing analog with Newtonian mechanics. And many of these depend on gauge choice, unfortunately. So we want to avoid it. Otherwise, we don't even know what we are doing. So we have to understand the choice of gauge. So the first thing is that we cannot define mass density or gravity, as everybody knows, because the equivalence principle says that it should be independent of choice of the coordinate system. But the first differentiation of the metric tensor will be 0 in the normal coordinate at one point, and therefore you will get mass density to be always equal to 0 if you define it. So it cannot be defined. But we still want to measure the total mass in a space-like region bounded by closed surface. This should be possible to define. In the old days by Einstein and many other people, you can only define it when you have an asymptotic flat system. The total mass can be defined. But now we want to define it for any region. So we want to find the gravity, the mass due to gravity on the surface enclosing this region. So this is the question that we try to answer, and this is called Quasilocal mass. So the energy or the mass that we want to measure within the space-time region bounded by this closed surface, and this should depend only on the quantities on this closed surface.
Do you allow gravitational radiation to be included within that surface?
Yes, everything included.
Even things moving at the speed of light.
Right. Everything included there. Okay. So we want to define that. Either the total mass and angular momentum, everything. Okay. We want to define that. So this is important. This in fact was listed as the major problem by panels in 1979 when we have a big special year conference in Princeton. And many people were on it. So I proposed, as a mathematician, I always want to write down what we want, at least minimum we want to be. So I write down the definition that it must satisfy. First of all, it should be non-negative. And also it's 0 for any closed surface in a flat approximate space. So this is a normalization we need. And then we want to say that it should be convergent to the familiar ADM mass that has been used by everybody up to now. And then, in the sense that if we see when the coordinate sphere that approach spatial infinity, it should be ADM mass. And then it should converge to bounding mass when the sphere diverges to color infinity. And then it should be equivalent to standard Coleman mass when you have symmetry, especially for SU2, sphere symmetry. So these are the minimum things that we have to satisfy. The reason is that this is obvious, the mass should be non-negative, and these two are important because we know ADM mass is good, and we cannot give that up. And body mass is pretty good also, so these two have to be true. So that's why we put that down. Well, there are many definitions was proposed. For example, Hawking defined the mass in this way. where sigma is the area of the surface, h is the mean curvature vector field along sigma. This mask is actually quite good and has been very useful, but unfortunately is rarely positive. Although Quasilocal and I find some cases where it's positive, some statement, but it's not positive, although it's useful. Okay, so it should not be called mass. As I said, Brown and York said n equal 1 and n equal 0 in the time symmetric case, where here assume kij equals 0.
Sorry, what's the mean curvature vector field?
Well, surface sitting in space-time, 4 dimensions, so you get mean curvature. 2-dimensional surface in space-time has a mean curvature, right? So variation of area in space-time is a element, is a normal vector to that in space-time. Okay, I actually worked on some case with Melissa Liu 10, 15 years ago. Try to use this as a definition. This is quite good. So I isometrically embed the surface into Euclidean free space. So just assuming you can do the embedding, which I will come back to this later. So you take a surface S, you isometrically embed into Euclidean free space, and you also the mean curvature that you take when you look at it in the Euclidean free space. And H is a norm of the mean curvature vector in the physical space that we are looking at. This we define it to be the mass. And this turned out to be quite good. We proved that rather non-trivially is always non-negative and all that. Unfortunately, this one is too positive. In some surface, in fact, this is strictly positive. In some surface, it
is there another problem that if the mean curvature equals the absolute value of h, then you get 0? So, for example, if you have a uniform mass distribution, wouldn't you get the mean equal to the actual?
No. We can prove that it's always strictly positive.
Strictly positive.
Yeah. But in the general case, I mean in this, well, okay. If E equals 0, the surface is very special. It's really 0. The trouble is that it's too positive. In some cases, which is supposed to 0, it turns out to be positive. So it's not good enough. Okay. But it says all the properties that I want, except that it's too positive. So now I come back to this definition, which I think is reasonably conclusive definition. Now this definition actually I think is very good, and I actually like to understand the physics of it much more. So given a surface now in a physical spacetime, in a 4-dimensional spacetime, I assume its mean curvature is space-like. This is not important. We can generalize it, but let's just assume that first. Now we isometric S into the Minkowski spacetime. Why do we want to do it? We want to have a reference to compare with. So I isometric S in here, and my observer is actually sitting in here. And isometric S into there, and I want to observe things here. So what is the thing we are trying to do? So I take this observer W sitting in R3,1, and then we can define a time-like vector field W bar along the original surface by using this definition. So let me show you the picture. There's a picture of that. So what do? This is the surface in the physical space-time. I isometrically embed it into R3,1. And I'm an observer sitting here, standing here. And I look at this surface, and I find the expansion of this surface when the observer is traveling this way is equal to h dot w. So these are the area expansion or contraction. This is the function, the measures here. So when photons go going out from this surface, bounce from this surface, this is the measures here, expanding or contracting. So what I want to do is that I want to set this one to be equal to a new gauge sitting on the surface, satisfied. The same property, the expansion or the contraction is the same at each point. That's what I want to assume. Okay. Then I can define my gauge by using this. This W bar can be defined using this. So So let me repeat. So I'm traveling here and observe the embedding here. I want to set this to be the same. Let me expanding here is equal to expanding here. And this allow me to define my gauge, which Brown and York said A equal to 1 and N equal to 0. Now it's no more 1 or 0. It depends on this observer, how they look like this thing. So let me repeat again. So I put my surface that I want to understand into R3, 1 isometrically. So the metric does not change. And from here, I define a gauge of N and N here. And this W bar mu is now a observer as a vector field along the surface.
Can an arbitrary vector field along the surface?
Okay, you mean here?
It varies at every. There's no sense in which it's constant.
This is not constant. W bar is not constant. It's only here is constant. In the Minkowski space, some use constant. And actually, we use any Killing field here. That's how we define angular momentum, define linear momentum, and all that. You take any Killing field, in fact, conformal Killing field will do. We can define what we want. This W bar is not constant. It is only here is constant. Well, of course, you can choose many different vector field here, but doesn't make sense. Only constant makes sense. I mean, Killing field makes sense. Okay. Now what do I do? I plug it back into the surface Hamilton that I mentioned to you. There are two
So
numbers.
those different choices of W's somehow gives you 4 momentum. Is that right?
Yeah, exactly. The different constant motion give you different the 4 vector.
But between energy and momentum, only the energy is supposed to be positive, right?
Well, as a vector, yeah.
So we might some kind of bound
actually,
eastward.
I'll come to that a little bit later.
Okay.
This is a nonlinear field, in the sense that the number I will get is actually not defined by 4 vector. It's actually a function only. It becomes a 4 vector when you are near weak field limit. If the surface is near spatial infinity, the function is defined by 4 vector. But when it's near strong field limit, when it's strongly interacting, it's not defined by 4 vector.
What about null infinity? Is it also?
Yes, both of them are not. Only now infinity is fine. Okay. Only near infinity is defined by 4 vector. But when it is in a compact region where the black hole is interacting, it's not 4 vector. It's not linear. Okay. It indicates the nonlinear phenomenon. Anyway, so this is the thing I defined before. And so there are 2 of them. One is on the surface itself in the space-time, and the other one is sitting in the Minkowski space-time. I take the difference to define to be my anything. But there's a very important observation technically, is that I have a very nice geometric interpretation of this guy. It turns out this guy is simply the integral of the mean curvature if I project the vector into a 3-dimensional space. The complicated thing that I wrote down on here turns out it's just integral of the mean curvature on here, on this projected vector. Okay? When I'm moving a W mu in this direction, I take a R field perpendicular to it. So the energy I define is this fellow. So N and N mu, I just choose a gauge for you. And this is the mean curvature that I said in space-time. This is the one you see in Minkowski space-time. I take its difference and I prove that it's always positive. So this is a very non-trivial proof. First of all, I prove this one is always positive. Since it's positive, I can minimize it. Okay? And this would be my surface. This is my energy of that quasi-local surface. Now here I get a bonus. In order to achieve this energy, I will find a isometric embedding of the surface into R3, 1. This is not just good to define the energy, but it also gives you a frame of how the surface looks like in Minkowski space-time to the observer. So the 2-dimensional surface will appear in a special form for the observer, depending on how you're minimizing it. So first of all, we can find out how the minimum E is given by equation called tau. This tau is actually time. So I project the surface in the Minkowski space-time on a R3 on a Euclidean space. Tau is actually the height function of that. So measures how it deviates from a flat space. And this is the fourth-order equation, which is elliptic, and you can prove that it exists. Tau always exists, and you can define it. So you have the unit solution tau, which defines the embedding. So this can be calculated, numerically calculated, and you can, and then therefore define the energy density now. So in summary, given a closed space like two surfaces in space-time, whose main curvature vector is space-time, we associate 4 vector to that space depending only on the first fundamental form and the mean curvature vector of this surface. So it depends only on the two-dimensional surface. It's independent of the space-time nearby, independent of the things that the three-dimensional domain that give rise to the boundary. The boundary gives rise to this surface. So in a way, it's a conservation law for those things, because I fix the surface and all the energy inside the three-dimensional domain is the same. It's given by the same thing on the surface. Okay. Now this recently we found the following thing, which I think is interesting, to demonstrate why we need to embed into Minkowski space-time. So let's take the K metric. It's just a demonstration of something interesting may come up. So I take the K metric, as you know, it looks like that. And then I write down the two surfaces defined by T equal constant, R equal constant. The line element can be written, and is that. And the Gauss curvature of the event horizon, and all this can be written down. And then you can find out, it looks like this form, the Gauss curvature. But the Gauss curvature turns out need not be positive. When the sphere is far away, it is positive, but not when satisfied the following property. When the angular momentum divided by m is greater than square root 3/2, the Gauss curvature could turn negative somewhere. So when the angular momentum is small, the total energy calculable for the surface that I just defined is about 2/4 of the irreducible mass. And this can be done without much effort when the angular momentum is close, is very small. But when the angular momentum is large, as you see here, angular momentum over m is bigger than square root 3/2. This turns out interesting because the surface need not be able to isometric embed into the flat Euclidean free space anymore. And I thought it could always be, but turns out we do the calculation, it cannot be done. Now I should say that this interesting statement. This metric, when there's negative curvature, we try to, this absolute symmetric, we try to isometric embed it into R3. I thought it can be done, but it cannot be done in the following sense. You expect if once it isometric embed in R3, it will be absolute symmetric in R3. And then you do the calculation assuming it's absolute symmetric. It turns out there's no solution to that equation. Now, of course, you may say that you may be able to isometric embed this guy into R3, which is not absolute symmetric. My co-author, Ludwig, thinks that it's possible, but I don't believe that it's true. Because this statement will violate a very famous, famous conjecture in geometry that you cannot do that. So let me not get into that. So let me assume, therefore, when A is large enough, this guy cannot be isometric embedded into R3. This gives me a puzzling answer. Near the ergosphere, things become funny for this Quasilocal mass. The tau function is actually 0 when the R is large enough, and identical 0 because we can prove that those embedding are good and give you a global minimum. But yet, when it's close to the within the ergosphere, when the angular momentum is large, we actually found that it cannot be impaired. And this also means that one interesting thing, the surface that's axisymmetric, when it is getting to this regime, it cannot be embedded in R3,1. So the frame that you see is different. The observer must have to do something because it cannot just sitting in R3 and the observer just go in the time direction only. It has to change. There's some boosting of the observer going on, which I still don't understand very well. But in any case, beyond that, already I think there are many other things published that we like to say. First of all, in the small sphere limit of the quasi-local energy that we just defined, it turns out the quasi-local energy has this form if the matter density is not equal to 0. This is what you expect. So in the limit, it gives rise to matter density when it's not 0. But when the matter density is actually 0, it gives rise to something interesting. It's the R to the power 5 times something called Bell-Robertson tensor. And this is a interesting quantity from the Bell-Robertson tensor. It occurs in many parts of general relativity where we use it to prove, say, Quasilocal and Kleiman's paper. And it's this limit that makes it distinction from many other quasi-local mass. For example, Hawking mass in the limit looks like that. It's not different from this one. And the Bell-Robertson tensor satisfies conservation law and is an important tool to understand what's going on. So now we can define other quasi-local conserved quantity by using different Killing field. Instead of constant vector field, which we say, we can take a Lie algebra of the Lorentzian group and take the dual element of it, and we can use this to define quasi-local angular momentum, also quasi-local center of mass, corresponding to the pairing of this.
Can you use all the BMS generators or just those?
Well, we hope that we can use it. I think we can, but the only problem is that we don't know whether we can justify their interest or not. The BMS generator.
But there's no canonical way to separate the angular momentum from the other ones, right?
Right. Well, you see. I'll tell you how we define it. Okay. Now, this is actually interesting by itself. Quasi-local quantity, as I mentioned, there's no density. But now we are defining it. So we have the tau function, which I mentioned, and we define the rho to be the quasi-local energy density defined this way. And we define the momentum density by using this thing. And tau plays a role all the way here. And turns out the optimal embedding equation that I wrote down earlier, the fourth order equation which looks ugly, becomes a simple one, is divergent of J equals 0. So on the surface itself, the two-dimensional surface, we actually have some kind of density and density, energy density and momentum density, etc. This rule.
So this it looks like a conservation equation,
right?
But without the time derivative.
Right.
So is it a steady state situation that you're thinking?
No, this object state. The surface is an object
because
state.
if there is flux of momentum,
but this is on the surface itself.
Only on the surface.
Only on the surface. This is what it is. So based on this, on the other hand, we can define the conserved quantity of sigma. So given any optimal isometric embedding as I defined, and any Killing field K in R3, so Lie algebra of the Lorentzian group, we define the quasi-local quantity this way. K dot T naught. T naught is the time-like Lorentzian transformation A in this way. This is this constant vector. Plus J, K times the tangential part. This turns out to be a good definition. If you use rotation vector field, this defines a quasi-local angular momentum. You use this, it defines a center mass. This actually turns out to be very good because the definition of definition even without quasi-local, definition of angular momentum is rather tricky because it may not converge when you write it as a total integral over whole space-time, over whole space. And there's cancellation you have to be sure. And somehow this definition take care of the cancellation automatically. And so we define it quasi-locally and take limit, it becomes a total angular momentum. So it satisfies several important properties, and this is obvious. And
sorry, didn't you write a paper in which you found an embedding of initial data in flat space?
The asymptotic vanishing is not strong enough for that example.
Oh.
Something to do with how fast it
No,
goes
but it
down.
was Minkowski space, right?
Yeah, I know. But the slice, the K, the
Okay,
induced.
so it's not for any surfaces,
Yeah,
it's
no,
for,
no, no.
for special
Yeah.
surfaces.
Okay. All the total conservatory values on any space that have a surface is Minkowski space-time, and that's important. And the total angular momentum and center mass turns out to be finite, which turns out to be not trivial to prove. And it says a very interesting quantity, which a priori is not clear at all. You define the center mass, you differentiate it, you see how the motion goes. It turns out to satisfy this equation where pi is the ADM angular energy momentum form vector. So it is a generalization of this equation. Now, why is it amazing? Because when we define this, they do not know each other in a way, and this is through the Einstein equation. So they have somehow fit together exactly what it was. Although the definition seems to be apparently different from each other completely. Now, the definition of angular momentum is difficult to do. Actually, how much time do I have?
5 minutes.
5 minutes? Okay, so maybe I can go into further standard angular momentum. Anyway, so the quasi-local quantities will approximate to these quantities, which is same as ADM mass and all that when we go to infinity. And the definition satisfies all the standard rules that we would like. I want to say a few words about gravitational radiation. So we take the Schwarz geometric and perturbate. So there are perturbations here, Q2, Q3, and it can be solved. The linearized Einstein equation is solved by separation variable ansatz. That's Chandrasekhar already did it, Q2, Q3. And then it said solved, you can be written in this form, and we solve the equation, the Relativity equation, and this all can be done by separation variable. And so on Schwarzschild space-time, we can therefore study the following property. I take a point which is distance d away from the black hole, and we study how it looks like. So basically, this is the hole, and I take a point which is here, okay. And then I study the quasi-local mass in this region. I want to see how it behaves. Well, it turns out to behave interestingly. We can study it by looking at the optimal isometric embedding. We can calculate everything according to what we did before, this non-trivial calculation. But then we did the following thing. We compare the quasi-local mass on the small spheres. Compare with the total quasi-local mass of the large coordinate sphere. It turns out they do not sum up to be exactly the same. So that means there's some nonlinear effect that it goes on in the quasi-local energy. And there are energy which are radially away in this way. And so basically that's what I'm doing. The picture I just saw is that you sum up all this quasi-local energy put out together. It's different from the total quasi-local energy of the large sphere. So it's not quite linear. Now, it turns out when I do a gravitational perturbation of the small sphere also, the quasi-local mass I just calculate on the small sphere vanishes to 1 over d squared. 1 over d vanishes in that integral. Then they give rise to a different kind of ways to measure the the gravitational radiation in the following way. If I choose a closed loop in infinity. So suppose in the center galaxy we have a black hole, and now we are measuring gravitational radiation at the Earth. I pick up a closed loop, an ellipse, for example, and I try to measure the flux of the gravitational radiation passing through this loop. That's what I'm trying to measure. And what we can do is that I can bound this closed loop by a two-dimensional surface. I measure the quasi-local energy in that. This turns out to be a well-defined quantity. And this, you can use it to measure the gravitational waves, the flux passing through this loop. So this is what we found out that you can do. So by making use of this loop with different geometry, for example, ellipse with different eccentricity, you can get different quantities that you want to measure out of the black hole. So I imagine you can do the same thing for Quasilocal, although we didn't calculate exactly there. So for example, in Quasilocal, you have angular momentum, you have mass. So hopefully by changing the closed loop in different geometry, you can actually measure what the angular momentum and all that is of the black hole, the K metric, by using this geometry freedom. Well, we did calculate it for some other things with more dynamics, but I don't think I have time to go into that. So maybe I just this last part is about anti-de Sitter space. We can do the same thing also, but let me not go into that.
So the last thing that you just very quickly here was the Badia metric that's of radiation in a spherically symmetric geometry. And so you can define also the mass of the radiation there.
Right. You can calculate.
This is very interesting because we were let's ask you afterwards.
So is this the kind of thing you can measure with, let's say, an advanced LIGO? And by advanced, I mean like way beyond what we have now. But could you measure this quasi-local mass within the sphere here on the Earth or coalescing black holes?
I do not know experiment, but what I can tell you what's the point is that you get a loop, you take a surface, enclosing it, bounding it, and you need to measure the geometry of this loop after the radiation, namely the mean perturbation. If you can measure it, then you can measure everything that I talk about, which should be possible. But it's very refined. So you take a membrane, you want to measure it, how it fluctuates after the radiation.
I see. So it's an effect that is after the flux of the radiation goes through.
How the mean curve changes. Okay. Presumably you can measure it.
I'm trying to think of how.
Yeah.
So how, if you take this spheres out to null infinity, how would these transform under BMS?
Oh, the Quasilocal mass? What do you think about it? Under BMS group.
Yeah.
We have enough problems to deal with. for the small group, the BMS group is huge.
It should constrain it, right?
Yeah. If I know what is a precise statement, I can demonstrate. It would be much easier. You can formulate a statement that I can demonstrate whether it's true or wrong. That would be much easier for me.
But is it completely diffeomorphic? It's not completely diffeomorphism, right?
It's not. Also, it depends on the high order thing when you do that calculation. See, I said the 1 over d squared, and then the lower order term and all that is probably coming under BMS group.
You mentioned that you can't put Kerr of large spin. You can isometrically embed it into R3, but I think it's been done for H3 or ADS3.
You can always do it in HP, but you cannot do it in R3.
Okay. But that doesn't work for your purposes?
Oh, well, you can do it in R3, H3 for negative curvature enough, but that's not what I'm trying to compare with. So the strange phenomenon is that when the sphere is large enough, it can all be done in R3, and we know exactly what the quasi-local mass is, tau is equal to 0 and all that. But suddenly within a small region, it cannot be done. And the sphere will have an observer seeing it in a very different way when it's near the ergosphere. So I found it interesting why that is like that. So something happens near the black hole that makes the geometry distort. You see, when I say the surface, a gauge for the mass, but actually it's not just the mass, the frame of the whole surface. Because I isometric embed in R3, and I choose a one that is optimal for this embedding. That frame is unique, and it gives rise to the geometry of the space-time, because it measures the whole thing.
Okay, let's say Yao again. So our second speaker is Professor Andreas Burkert. He holds the chair for computational astrophysics in the University of Munich. And his interests went from dark matter to formation of stars, planet galaxies. And today he will tell us about the title has changed.
Yeah,
Was
was
it-
it a different type?
There was a bathtub.
Well, who
That's
cares?
the right
Who cares what the title is?
Okay.
Galactic gas as well, yes, well, I don't.
There was something to do with the
There was a
bathtub.
bathtub, remember?
Well, what is this? So it's the right talk, I think. Okay, so thanks for inviting me to give a talk, and I will try to give something which I find quite exciting. It changes day by day, so tomorrow might be different, but today it's the bathtub, and I would like to motivate it with the following idea. If you look at the universe and galaxies, then it's a continuous evolution, and there are many unknowns, but one thing is correct, namely that somehow the mass is conserved, and so you need to kind of fulfill the equation of continuity, and if you don't do this and something is wrong, on the other hand, just using this equation you can explain a lot of things. You get so many constraints that it's just worth working on this, and I'm not that good in mathematics, so that's enough for me. Just solving this and trying to find out the implications for the universe is enough for the moment and keeps me busy for many years. And I would like to demonstrate this with an example today, which is a galaxy. A galaxy is so to say, is a conveyor belt. In the sense that you have the universe and the density there is tiny, and then inside this galaxy, so the galaxy accretes gas with density, let's say 10 to the minus 4, 10 to the minus 6 particles per cubic centimeter from the environment, accretes it, and then at the end you might form a central black hole, you might form a star, where the densities go up to above 1 particle per gram per cubic centimeter. So there's more than 30 orders of magnitude change in density, 10 orders of magnitude change in volume, and you need to take all of this into account if you really want to understand how the universe evolves and what's going on in such an environment and how stars form and everything like that. So what people have been doing in the past is they isolated the problem, like what you did. You make a toy model and you solve that. Now the question is, how good is this? You know, if the universe, if this galaxy is strongly dependent on boundary conditions, then isolating it makes no sense, because the boundary conditions and are everything. So we'll better figure that out before we waste time on some problem which is maybe interesting, but which doesn't really tell us anything about how the universe evolves. And I would like to tell you today that actually everything is boundary. So if you really want to understand how you formed and our galaxy forms, you need to take the universe into account, and you really need to couple all of these scales, 10 orders of magnitude in size scale to get it right. And that is a bad result, but what can't be helped. So it has to be solved. And maybe here, this is the environment where we are best suited to do it, because it requires an enormous amount of expertise on all scales. Now, why did I put this up? Molecular phase of the ISM. Yes, I would like to demonstrate that on two ways, and the first one is actually just to give you an idea what we are talking about. A galaxy is an environment where stars are forming. And that's what you can see over here. You see, of course, lots of stars, but you see that the space between the stars is filled with gas. You have a diffuse gas component, and then they have a very dense gas component. This is basically obscuration of stellar light behind. This kind of, it's the pipe nebula, which is obviously, you can easily see the pipe here and the foam in the pipe. And at these higher densities, gravity becomes important and stars are forming. And so if you want to understand how stars form in the galaxy, you have to go to these dense environments and study them in greater details. And so the standard idea which we had of a galaxy evolving is the following. You have the galaxy that has a lot of gas. We call it interstellar medium. Then if the gas condenses into these dense structures, stars are forming. The stars explode as supernova. You can see here the stellar feedback, and they feed metals and hot gas into the interstellar medium, keep it running, and you go through the cycle, and then you solve it, and you find some equilibrium state, and you basically then can understand how a galaxy evolves and how we formed, and so on and so on. And so we have this closed box, and we started the self-regulation. Now, that's an idea, and we have been doing it for many times. I started my whole career on this. I even got a job, my basically professorship, doing the wrong thing, but we didn't know much better. Well, if you have this galaxy and you start with initially all gas and form stars, and without much thinking, if you just solve the equation of continuity, what happens if the gas mass has to go down, and the star formation rate then goes down, and the stellar mass has to go up. So you expect that the smaller, you expect an anti-correlation between the star formation rate and the stellar mass. Because the more stars you have, the less gas you have, and less stars you can form. And that's something which we have been doing all the time. Now, it turns out that is not that easy, and it doesn't really work. And this is shown here by this diagram, which shows the star formation rate of galaxies as a function of the molecular dense gas mass where stars are being formed. So you see each point is a galaxy, and you can see that the star formation rate really increases proportional to the gas mass, which makes a lot of sense. The more gas I have, the more stars I can form. And it turns out, and this is actually one of the interesting puzzles, the star formation rate is just proportional to the gas mass divided by a time scale. Now, at first, this is trivial. Why is it trivial? If you look at star formation in a galaxy, then you sum up over many, many different regions of star formation. And then the history of each single region is of no importance anymore, because you average over many things. And then the central limit theorem tells you that at the end, the star formation rate in a galaxy should just depend on some average quantity, which is the total gas mass you have, divided by an average time scale, which is the star formation time scale. So that is clearly, but this clearly easily understandable. But the funny thing is, this time scale is 10 to the 9 years. Now, 10 to the 9 years is short compared to the age of a galaxy, which is 10 to the 10 years. And so if you would have a galaxy that formed early on and then was turning into stars with this kind of time scale, then the galaxy should have burned out by now. All galaxies should have burned out by now. And that's not what happens. Galaxies are happily forming stars today too, and that tells us that actually the galaxy is not a closed object. The galaxy is actually continuously replenishing gas. It must accrete gas from the outside, and we have to take this into account. And then there's another issue which actually puzzled me a lot when I first saw this, which is the galaxy main sequence. Each of these regions, this region contains a lot of different galaxies. And we plot here the star formation rate in a galaxy as a function of stellar mass. And what you see, when I saw this, I thought people had gotten it wrong. I thought this is gas mass, but it is stellar mass. What you see here is something which is just the opposite of what I said initially. When you make the galaxy more massive in stars, the star formation rate is not going down because you have turned more gas into stars. The star formation rate is going up. That means as a galaxy grows and forms more and more stars, it even forms, if the rate goes up, it forms even more stars. Now, if you have an isolated galaxy, that's impossible. Because the more stars you have, the less gas you have, the smaller the star formation rate. But what you see here, the more stars you have, the even more star formation you have. And that's just the opposite of what you can think of. In fact, you can quantify that. You can show that the star formation rate is proportional to the stellar mass, not to the necessarily to the gas mass, times the dependence on the cosmic redshift, which is a strong dependence growing as to the power of 2.5. Now, that tells you that galaxies somehow, when they become more massive in stars, need to gain even more gas for the star formation rate to increase. And that requires that you take into account the boundary conditions and inflow. And indeed, that's something which is in very good agreement with the cosmic evolution of structure in the universe. Here you see how the gas accretion rate onto a galaxy is if you just simply take structure formation and you look at the dark matter growth and you say that the gas mass that falls in is proportional to the dark matter mass, which is growing in the galaxy, then you can show that you expect this dependence on the total mass and this redshift dependence. And you see it's in perfect agreement with this kind of star formation rate. As if the gas accretion rate directly feeds onto the star formation rate, which demonstrates that the galaxy indeed is not an isolated system. The galaxy knows about the environment where gas is falling in, and that's basically what determines its evolution. So the question is, can we understand it with a simple term? And that leads now to this bathtub idea. And I like the bathtub because bathtub is everyone should do it. Probably when you had minus 20 degrees Celsius, whatever your Fahrenheit, you were sitting in the hot bathtub as long as you could get the water up to some temperature at that kind of cold weather. Well, you can do it in the following way. You can say, you look at the mass budget, and that's all I need in a galaxy. The mass budget, mg as a function of time, changes because you accrete. There's an accretion rate, and it goes down because you form stars. We just learned the star formation rate is the gas mass divided by 10 to the 9 years, this universal constant, which we don't really understand why it is 10 to the 9 years, but it seems to be so. Now, there's a certain fraction of the gas that turns into stars is returned by supernovae and winds and so on. This is roughly 50%. And you also remove a lot of gas through wind, which blows out the gas of the galaxy. The removal rate is proportional to the star formation rate. So this is order 1. So you see, you get here something like 2 minus 0.5, which is 1.5. I think I did put it in. No, didn't put it in. So you have here something like 1.5. And so now what you can do is you can solve this equation and you find this result. The star formation rate is this kind of constant here times 1 minus e to the minus t over tau. And you see immediately what happens in the initial phases when you say, let's say you start with no gas, the gas mass is slowly increasing with time, and then if you wait long enough, then this term is negligible, and you basically get a constant value. It doesn't really matter how you start, you will always, of course, approach this constant value over here. And you see this constant value basically assumes that the star formation rate is equal to the effective accretion rate. It's just given by this quantity here. This is the constant to a third time the accretion rate. So that actually means that the star formation rate in a galaxy is not at all dependent on the intrinsic process of star formation. The time scale of star formation does not actually matter. The star formation rate in a galaxy is just simply given by how much you accrete. And all the physics of star formation does not enter the star formation rate equation in a galaxy. It's purely a boundary condition and has nothing to do with the internal properties. Now, of course, it's different with the gas mass. The gas mass is the star formation rate times this kind of universal constant, the star formation timescale. So the gas mass, of course, depends on the intrinsic properties, which is the star formation timescale. And so basically what it is, this is like a bathtub. In the early phases, when the galaxy starts to accrete gas, it has to fill up. And while it fills up, the star formation rate depends strongly on intrinsic properties. And then the galaxy reaches a certain equilibrium state, where what comes in goes into stars. That's basically if you wait too long and you go and have a phone call or whatever, and you fill up and you leave, then what comes in goes out. And what goes out here goes into stars. And then it's strongly dependent on the boundary condition, on how you accrete gas from the intergalactic medium. And we are basically in this phase because the galaxies are all older than one star formation timescale. How big the gas mass in a galaxy is depends basically on the star formation timescale, which determines how big your bathtub is. Small star formation timescale means that everything that falls in immediately goes into stars. The star formation rate is still proportional to the inflow rate, but you can't build up much of a gas in the galaxy because it turns into stars immediately. And if you have a big bathtub, then the star formation timescale is long, and then it's the opposite. So let me just see. I just need to see whether this is really the right So the bad news now is that a galaxy cannot be treated as an isolated system. The star formation, the gas mass in a galaxy, is given by what falls in. And the details of the history of star formation in a galaxy is all dependent on where the galaxy sits, in which environment it sits. And if you don't get that right, you can really ever work out what happens in the galaxy. So that's the first thing. The second question now is, when we go into the galaxy, into more details, do we still need a bathtub? Do we really need to couple all kinds of processes again? And that again leads me to this question of the star formation timescale. I told you, if you look at galaxies, then wherever you look, gas turns into stars on a timescale of 10 to 9 years. Every galaxy does that. The question is, this is a clock. What is the clock? What is the nature of the galactic clock? If you just look at all processes and everything I see in a galaxy, is there a process happening on 10 to 9 years? That's very fundamental, because we see this everywhere. There's no galaxy which is not doing that. Now, the most easiest way is to say the orbital period. Galaxies are rotating, and a clock rotates. Well, I can see this. Well, digital clocks are not rotating anymore, but I mean, a clock usually is a rotation. Yeah, that's we get an orbital period, and then you get 10 to 9 years. The orbital period is always 10 to 8 years. I then simply say the star formation has a certain efficiency of 10%. Then I get 10 to 9 years. That is something which a lot of people have been doing. I've been doing this too. I wrote several papers on that where I assumed this. Now we have done a recent compilation where we correlated the depletion time with the orbital time. So you see the depletion time is roughly 10 to 9 years, and the orbital time varies by more than an order of magnitude. And then we fitted this with a correlation, and I have to say the correlation is not very good. I mean, so this model is not working. But there is no other clock I know of. So we have no idea in this end how to explain this kind of depletion time state. Well, maybe it's a local process, because as I told you, stars form in the dense parts of the molecular region, or in the interstellar medium. These are molecular clouds, that's where stars form. Maybe you find the 10 to 9 years in this kind of region over here. And I just want to show you how beautiful these regions are. I usually get this kind of teaser every year from Joao-Alves, and here he wanted me to explain this feature here, which I thought is something, a cloud in front of us, and you see the shadow, but it's not, it's actually a hole in the cloud. A very funny hole. And how do you get in this very rich environment a hole is a big puzzle. And so that's what he gave me as a teaser, just to work about. It shows you the complexity. There's something else. If you look at all of these filaments, you see that they follow a nice power law correlation. The mass of gas in the filament with the length follows a power law, which goes as a power to the 1.7. And it covers, if you look at the mass, it's 6 orders of magnitude mass and 2 to 3 orders of magnitude in length. We have no idea why these filaments are all connected to each other, and the power law has not been explained at all, why it is 1.7. It's kind of in between what you would expect. But anyway, we know a lot about these structures. And now you can do the following, okay? You know the mean densities of these filaments where the stars are forming is 100 particles per cubic centimeter. And you can try to find the this 10 to 9 years in it. Now you can do the following. You can look at the collapse timescale. The collapse timescale of gas in these regions is 3 10 to 6 years. And so you can say, okay, can I really explain my star formation rate if I look at this collapse timescale? The problem is, if you look at the molecular regions, the total mass in molecules is 3 10 to 9 years. If you divide this by the collapse timescale, you get a star formation rate of 1,000 solar masses per year. So this cannot explain what we observe, because the observations show a star formation timescale, the star formation rate in the Milky Way of 3 solar masses per year. That's why you get this kind of 10 to 9 year depletion time. So how can you solve it? Well, you can say in 3 10 to 6 years I'm collapsing. I want to get out of 3 10 to 9 years 3 solar masses per year. So what I need a very low efficiency. Yeah. If is that correct? No, that's not correct. Well, you know what I mean. 3 and 6 years. No, this is. No, that's okay. That's okay. I need an efficiency of 0.03%. If only 0.03% of this molecular gas turns into stars, then I get this kind of star formation rate. Well, that does not really work, because if I look at star forming regions, and if I calculate how much gas stars I have in these regions compared to the amount of gas I have, then this is in this ballpark, which is about 3%. It's 0.3%, not 0.03%, which is down there. So the efficiency of star formation is much larger than what I expect in order to explain the star formation rate and go from 3 to 6 years to my 10 to 9 years. So this doesn't really work. So the question is, how else can you solve it? And then we try, well, you see, I'm now hand waving. You will continue hand waving till the end. I'm lost completely because we don't know the answer. I just want to tell you what is not the answer. And maybe there's a non-trivial answer to this. Well, okay, you can say, okay, maybe not all of this gas is forming stars. Maybe it depends on the details of star formation, and then out of that comes my 10 to 9 years again. Well, the details are shown here. If you look at the torus molecular cloud, you first of all see something very fascinating. You see there's a lot of molecular gas that is diffuse. And in fact, you can see here big whirls like that, which are probably something like Kelvin-Hamilton instabilities and so on, that mess up this diffuse gas. And only in the most dense parts of the gas do you form stars. So you might say, if you want to get these kind of 10 to 9 years, maybe we should have to focus on these very dense regions alone, and not on the diffuse regions. Well, you can do the test. You know how much mass you have in the dense molecular material. It turns out to be 10% of the diffuse molecular gas. Indeed, you have less mass. If you have less mass, then the star formation rate should go down. So we have 3 to 8 solar masses of gas in the dense gas. The problem is, in the dense gas, the densities are a factor 100 higher than in the diffuse molecular gas. And at these densities, the free fall time is now a factor 10 smaller, because the free fall time goes as the square root of the density, 1 over the square root of the density. If you work out how quickly this dense region is forming stars, it's again 10 to 3 solar masses per year, and not the 3 solar masses per year. So what you need again is you need again an efficiency of only 0.03 or 0.3% of star formation in these dense regions in order to explain the low star formation rates in galaxies. Now, dense regions should collapse much more easily than diffuse regions, and having that low efficiency doesn't make sense either. So we are still stuck with the problem, and we still don't know how to solve it. Now, if you look at the dense regions, look at the mass in the dense gas, and compare it to the mass of stars which you see in these dense regions, you find something interesting. You find a very nice correlation. That means the more mass a dense region has, the more stars it has. And that is, when I saw this, very interesting, because it means the more stars you have formed, the even more gas you have in a dense region. And that wouldn't work if your dense region is an isolated box, and you start up with a lot of mass and no stars, and then you turn this mass into stars. Then you would expect something like that. The mass of stars go up, the mass of gas goes down. But what we see is the opposite. We see the more stars we have formed, the even higher the mass of gas in the dense region we have. And that reminds me of my galaxies, where I saw the more stars I have formed in a galaxy, the even more gas I have in the galaxy to form even more stars. And in the galaxies, I explained that with the Bathtub model. I said a galaxy is not isolated. The galaxy is actually continuously forming, creating material, and that's why it can crank up the star formation rate even if it has already formed a lot of stars. And the same seems to be true in these dense regions. That is only possible if the dense region is continuously accreting material from the environment, and we cannot actually understand star formation in the molecular cloud in an isolated way.
Andy,
Yes?
are you sure about that? Because if you have an efficiency of 0.1, right, then the number of stars may not, you keep making more stars, but it may not decrease the total mass of the cloud very much. Right?
Well, it would be these are 2 orders of magnitude. That makes a difference. You know, if I turn a 10 to the 4 solar mass cloud into stars, when I have 10 to the 4 solar mass of stars and 10 to the 3 solar mass of cloud, the mass of the cloud should be, the gas mass of the cloud should have gone to 0.
I'm not sure why this isn't just trivial. You get a bigger cloud, you get more stars.
Yeah, and the cloud doesn't start big. The cloud always starts from 0. The cloud starts here. It doesn't start here magically from nowhere. It starts here, and it grows to more mass. And when it grows to more mass, then basically, if let's say if the cloud would have started here with 10 to the 4 solar masses of gas, no stars here, and turned all these 10 to the 4 solar masses of gas into stars, then by the time it has these stars, the mass would be there. You would expect this correlation, and you see this correlation. So basically, how can you solve this? And how can you explain this 10% of star formation in this dense region? That means 10% of the mass is in these stars. Well, the answer is that the past history of star formation, which you see here, doesn't tell you anything about the present cloud mass. The present cloud mass is something that happened with the environment, and the past history of star formation tells you what happened before and not what happens right now. And that requires a continuous inflow, and so that's why I now would propose this kind of bathtub model for the interstellar medium. And again, I would like to do it in the following way. Let's focus on the dense mass of 3×10⁸ solar masses, which we have in the interstellar medium, and assume that is all you have. And assume that the dense gas mass turns into stars on the free-fall time. Then you get this kind of exponential decrease in the dense gas mass on a timescale of 3×5 years. And if you want to have a star formation rate which is observed right now, then you need an efficiency of 0.3%. But of course, you run out of dense gas mass very quickly. So you have to reform the dense gas mass, and you have to accrete onto the clouds in order to solve this. Now, this is, if you do this for each individual molecular clouds, you can demonstrate that this is also not the correct prescription, even if you just now replace this by the mass of the molecular cloud. Why? Well, if I look at a star-forming region like that, then I see the following age distribution of stars. This is from Parla 99, a long time ago. People actually never really bothered about that till recently. You see the age of the stars. These are the youngest stars, these are the oldest stars. And you see that the star formation rate has been changing over time, and you can plot that as an exponential e to the t over 2.6 years, 2 times 10 to the 6 years. Now, this is not really doing what you would expect if you would have a gas cloud and it turns into stars. First of all, the time scale of star formation is much longer than your free fall time. That doesn't really work. And the second problem is that the star formation rate is actually increasing with time instead of decreasing with time. And that means this torus region hasn't been there from the very beginning, condensing into stars. The torus region has been building up while star formation happened already in the region. So the torus region has to be connected to the environment like we had in the galaxies as a whole. And so we have to write the history of the star-forming region in a completely different way. The dense gas mass in the star-forming region decreases because stars turns into stars on the free fall time, but it increases because you have continuous accretion. And if you then solve this, you get again the same bathtub prescription as for a whole galaxy. The mass of the dense region is given by a constant times 1 minus the exponent over e to the minus t over the free fall time. And what you see is in an early phase, when the molecular cloud is forming, the dense gas mass increases with time, and the star formation rate is also increasing with time, because you can neglect it. But if you wait longer than the free fall time, which is only 3 to the 5 years, which is short compared to the age of molecular clouds, the dense gas mass and the star formation rate in this molecular region is actually only given by the accretion of molecular gas. The star formation rate in this region doesn't know anything about how quickly the dense gas mass is collapsing. All of this free fall time plays no role anymore. It's a boundary condition. The amount of dense gas you have, on the other hand, depends on the accretion rate times the free fall time. And so we see basically that the star formation rate is, in a galaxy, is not dependent on the dense gas mass you have, or its collapse time scale. The star formation rate in a galaxy is dependent on the production rate of dense gas, which is this accretion rate, which is a paradigm that tells you that you need to take the whole dynamics in a molecule in a galaxy into account in order to understand how stars form and how much dense gas you have. You need to understand how quickly you generate dense gas, and that determines the star formation rate. And you can't simply take the mass of dense gas you have divided by a time scale. That gives it the wrong impression, because that's not what of this great importance. So the star formation rate depends on the various processes that drive the flow of gas through the different medium phases. Now, the question is, can we prove this kind of model? Can we prove that a galaxy as a whole is actually turning into stars and evolving because of its accretion rate from the intergalactic medium, and that the individual time things that go on in the molecular cloud are not determined by the cloud itself, but by the various processes that feed material into the molecular cloud? And I found one proof, which I want to show you right now, and then I'll stop. Basically, as I told you, there is a diffuse gas component and there's a dense gas component where the stars are formed. And it turns out that the dense gas mass, as I said before, is 10% the diffuse gas mass. Now, at first you might say this is maybe somewhere such, but it might be different somewhere else. But if you look at many star-forming regions, you basically can demonstrate that this seems to be true on average for all star-forming regions. There's a big scatter still. It also depends on where you find your boundaries. But in general, the dense gas mass is always only 10% the diffuse gas mass. The question is, why is that so? Why is the dense gas where the stars are forming 10% the diffuse gas? And it turns out in this kind of bathtub prescription where the flow of gas determines star formation, and not what is inside the dense gas at the moment, can explain that very well. The diffuse molecular gas has a mean density of 100 particles per cubic centimeter, and the dense gas has a density of 10 to the 4 particles per cubic centimeter. The free fall time goes as 1 over the square root of the density. So the fall time of the diffuse gas is 10 times the free fall time of the dense gas. This is 3 to the 5 years. This is 3 to the 6 years. Now, we can assume an equilibrium condition if we assume now that the diffuse gas is feeding continuously the dense gas. That means we have flow of gas into the dense region, and then in this dense region, this gas turns into stars on the free fall time of the dense gas, which is 3 to the 5 years. And we assume an equilibrium because the timescale on which the feeding happens is longer than the timescale on which the dense gas turns into stars, and that is actually what we showed before, an equilibrium. And then the bathtub model would say that the mass of dense gas which we have is given by the infall rate of diffuse gas by the accretion onto the dense gas times the free fall time or the condensation of the dense gas. But the accretion rate or the infall rate of diffuse gas into dense gas is given by the mass we have in the diffuse component divided by its free fall time. That tells you how quickly the diffused gas turns into stars. If we multiply that with T free fall of the dense gas, and then you see if you now take the deviation, derivative of m dense over diffuse, which is 10%, this is equal to the free fall time of the dense gas divided by the, wait a minute, the fall time of the diffuse gas. It's longer, yeah. The fall time of the dense gas divided by the free fall time of the diffuse gas. And this is exactly 0.1. And that demonstrates that the diffuse gas is continuously forming dense gas, and this is continuously forming stars, and you're in this bathtub situation where this kind of is true, and that is basically telling us how star formation happens, and we can never do it in isolation. So if you now look at the mass of dense gas as function of time, this is our solution of the bathtub equation, and this is the time scale as function of the free fall time of the dense gas. Then you see that we have this initial crank-up phase, which is this part over there, and then we have a phase where the dense gas mass is not changing anymore because it's just given by the accretion rate, which for time scales of the free fall of the dense gas is constant. The star formation rate, of course, is a fraction of this, is efficiency, which is given down there. And this is very interesting. The gas mass has reached an equilibrium. It is not changing in the equilibrium, in this equilibrium phase anymore. But the stars that you form are continuously increasing in mass, because this is an integral over the star formation rate of the history. So the ratio of the gas you have divided by how many stars you formed is a sensitive clock of how old the system is. Now, what the observation shows, if you look at star-forming regions, then on average the mass of stars we see in these regions divided by the mass in dense gas is 10%. Which means when this red curve, which shows you how the stellar mass is increasing, reaches 10% your gas mass, which is this dotted line, then you have reached basically a phase where the molecular cloud is breaking up. That's the current typical age of a molecular cloud. Now, this is the efficiency per free fall time of star formation, which you need, which you have, which you can assume as you want, and just simply to explain your star formation rate. The star formation rate is the accretion rate times the efficiency per free fall time. And you see, if you have an efficiency of 1% per free fall time, then you basically reach this kind of threshold, which is observed roughly at 10 free fall times, which is 3 to 6 years, which is very reasonable. If you have an efficiency of 10%, then you reach it much earlier. So that tells us that per free fall time, the efficiency of star formation in the dense region can only be of order 1%. Now, you might wonder whether this is any problem, but it is not any problem. Now that I want to show here again. Now here I plot this mass in stars divided by the dense gas mass as function of time. This is what we observe. This is 10%. And this is how in our bathtub prescription the stellar to gas mass goes up. As I told you, gas mass reaches a constant, stellar mass is continuously increasing with time. Now this is for an efficiency of 0.005%, 0.1, 0.001, 0.5%, 1%, 2%, and 5%, assuming this collapse timescale of the dense gas. So you see immediately these are typical ages of star-forming regions, and you see you can explain this kind of regime if you have an efficiency between 0.005 and 0.01 per free-fall time. You now might say, okay, this is too low. I told you the efficiency can't be that low in the star-forming region. But this is the efficiency, that means here which fraction of, that tells you how much fraction of the gas turns in the stars over 3×10⁵ years. Yes. And in 3×10⁵ years, you cannot really form any stars. It's a very, very short time where rarely one little core can collapse. And if you then wait for 10 free-fall times, which is typically the age, or 20 free-fall times where we begin to see star-forming regions, actually what the typical age of the star-forming region is, then the overall efficiency, just looking how many stars have formed compared to the gas mass which you have, turns out to be 5 and 10%. And so that is in very good agreement with the observations. So efficiency appears high simply because star-forming regions live for timescale much longer than the free-fall time. They can live for timescales much longer than the free-fall time because they are continuously fed by new material, so that the gas mass is not changing, while the stellar mass is kind of growing and growing. And so then we can basically get all of this in equilibrium, and we can explain what is observed. So to summarize all of that, I want to do this over here. I think galaxies and star formation in galaxies is a boundary condition. The star formation is in the whole galaxy, the gas mass in the whole galaxy is determined by what is falling in. It's basically the accretion rate into a galaxy. And if we want to understand how the stars form in a galaxy, then we basically have to know how gas accretes onto individual molecular clouds. And this accretion onto and the flux between the various gas phases determines how stars are forming. How all of that is then connected such that at the end the global star formation timescale of the molecular gas comes out to be 10 to 9 years. This universal clock is something which I don't understand at all, but somehow maybe if we put all of these various phases together, going from the intergalactic medium out to the densest region, it might pop out. And that's it at the moment. Thank you very much.
Since this is the Black Hole Initiative,
Yes.
there is one puzzle that I challenge you to solve, and that is why the amount of radiation produced by stars in the universe is comparable to the amount of radiation produced by black holes.
Oh, really?
Is that a complete coincidence?
Well, that's a very good question.
Maybe related to the feedback.
That is a very good point. But then the black holes have to know how many stars are forming.
So there is some interval.
Or, well, there is, I know the amount of...
How close is it?
Within a factor of 2.
But you only talk about central black holes. Because
Yes.
the other black holes we don't
Yeah, they
even
don't
see.
produce much.
So,
They don't produce
no, but that makes a lot of sense because the central mass, the mass of the central black hole is proportional to the mass of stars you have in a galaxy.
True. And then the
So then
but,
must
but
be the
why?
same.
Why is that? So explaining that would be an interesting.
Why is the central black hole mass? Actually, the central black hole mass is more proportional to the dark matter mass.
Okay.
So,
why?
so actually, there's a big variation in galaxy stellar mass, and then the black hole mass doesn't correlate it well. But if you correlate the black hole mass with the dark matter mass, it's a very good correlation.
So
And
understanding that would be nice.
well, because the dark matter mass is not radiating, and that wouldn't make much sense. Yeah. But I think on average, it's indeed true that the more massive a galaxy, the more stars you have, and the more black hole you have. But I agree with you. Why is it so? I don't know.
That's for you to solve.
Very good.
Oh, actually, we have a talk at 3:30 on the issue of on answering this,
Supermassive
addressing this
response
question.
feedback. Some of these questions.
Yeah, but that will be at the CFA.
Very interesting.
Okay, well, let's take one speaker.
Probably